In this video, we will have a short brainstorming around the concept of privacy. Out of this brainstorming will naturally emerge a mathematical definition known as differential privacy. Imagine you're sending an image to some website on the internet, like Facebook, Google, or some other kind of survey. You have essentially no guarantee about how your data will be used, and this might eventually have a highly negative impact on your life. For instance, the picture might embarrass you for your upcoming job search, or an analysis of the picture might allow your insurance company to detect a cancer you have recently been diagnosed with, hence leading to an increased insurance fee. Now, a basic definition of privacy would simply be to prevent any kind of data be given to any person or entity you do not trust. And this is a perfectly reasonable demand. However, you might still want to share some data with entities you do not fully trust. This is typically the case for epidemiological research, where data from patients could allow for future health breakthroughs, which would benefit not only you, but everyone else as well. Data from patients are both highly sensitive and potentially highly valuable for all of society. In this context, could we still guarantee privacy while allowing for useful exploitation of patients' data? Of course, the answer is no. So the next best thing is a trade-off question. How much privacy needs to be sacrificed in order to obtain some useful exploitable results? And this question itself leads to another question, namely, how can we quantify a loss of privacy? This is actually precisely the question that differential privacy provides an answer to. Now, I will be giving the mathematical details in a future video, but roughly, differential privacy is characterized by two measures of privacy losses, usually written as epsilon and delta. The smaller these are, the greater the privacy guarantee. And importantly, differential privacy satisfies two fundamental properties. First, it is robust to post-processing and combination with other public data. No matter how an attacker manipulates the data released by a differentially private mechanism, and no matter how he'll combine it with available public data, the attacker will not be able to retrieve more than an epsilon delta differentially private information about you. Second is the composition property. If an attacker exploits data from an epsilon 1 delta 1 differentially private mechanism and the data from an epsilon 2 delta 2 differentially private mechanism, no matter what kind of cross computations he attempts, overall loss of differential privacy will be provably at most epsilon 1 plus epsilon 2 delta 1 plus delta 2. Now, this video surely raises many questions, such as what is the formal definition of differential privacy, how should epsilon and delta be interpreted, and how can we construct epsilon delta differentially private mechanisms? Unfortunately, or not, these will have to be addressed in future videos.